My name is Dan Yolneny, and I'm the founder of SemiWiki, the open forum for semiconductor professionals. Since going online in 2011, SemiWiki has registered more than 200,000 active members. If you're not a member of the SemiWiki community, please register as my guest. I hope to see you there. Today's webinar is titled RISC-V Instruction Set Architecture, Enhancing Computing Power. The speakers today are Bing Yu, Computer and AI Architect from Andes Technology USA Corporation, and Gareth Baron, Applications Engineering Director of Menta SAS North America. If you have questions, please use the question tab and we'll answer them during the Q&A at the end of the presentation. Okay, let's get started. Over to you, Bing.
Thanks, Dan. Good morning. Thank you for joining this webinar, Design Software Defined SoC. My name is Bing Yu. I'm the Director of AI Compute Architecture at Andes. I'm here to describe the trend and detailed technologies in chip design that have contributed to the success of these two companies. The first trend is that currently there's a rapid adoption of the RISC-V ISA. And RISC-V ISA have different layers, starting with the basic instruction layers, which is implementing most of the processors, RISC-V processors. And you can optionally implement standard instruction extension, depends on your application needs. And also that you can design the custom instruction extension as well. The extensible ISA provides several benefits. One is performance enhancement. The other is power reduction and also cost cutting as well. The second trend is towards software-defined products, represented by software-defined vehicle, which can be easily updated by the new software. Increasingly, the logic gate within the semiconductor device in the cockpit electronics and engine control need to be updated with secure patch. Also need to be accommodated for the advancement in communication protocol and adjust parameter for engine wear and tear. And this is where Menta's embedded FPGA come into play. With me today is Gareth Baron. He is the Application Engineering Director at Menta North America. He will describe how to integrate Andes custom instruction with Menta's embedded FPGA to achieve the in-system configurabilities. Here is the agenda from Andes. We're going to talk about why custom instruction, what benefit does that bring, and also we're going to talk about the high-level architecture of Andes AX45 MPV, ACE, and ACE RVV extension. And the ACE is a scalar part of the custom instruction, and the ACE RVV is a vector part of the custom instructions. But today, we're going to concentrate on the scalar part only, which is Andes custom extension ACE. We're going to talk about its features, and we're going to describe how you can design this instruction with the tool that Andes provided to you. And we'll also going to give you an example. In the ever-increasing requirement and complexity at all levels of performance for the following applications like ADAS, AI/ML, networking, sensor storage, and AR/VR, they all have a very complex requirement with performance and power efficiency. The SoC designer tried to find a balance between absolute efficiency by using a fixed hardware solution, and also that some of them had to deal with a flexibility, which is using the extreme high speed overpowered CPU, which could be very expensive. So the custom instruction can be a good trade-off for them. It provides much higher performance, much lower power. Yeah, it's very configurable. And one of the side benefit is easier protection for your software IP because this custom instruction is not exposed to the user. With the above benefit, extensible RISC-V is ready for the domain-specific acceleration. And the key to the custom instruction is to identify the hotspot to speed up. And also, you need to have a good tool to help you to do exploration, design, and verification of your custom instructions. Yeah. Here is NDIS AX45 MPV architecture with ACE and ACE RVV. On the top, the AX45 MPV is an 8-stage dual issue pipeline. And in the middle is a vector pipeline, which the vector instructions issue in the EX stage of the main pipe to the vector pipe. And in the bottom is the ACE pipe stages, which is being issued in the write back stage of the main pipe. And one important feature is the streaming port. It provides a high-speed interface between the external memory and the vector units. Let me describe to you how it works. You design the ACE instruction to send out a command to the command port to the external custom coprocessors. And the coprocessor, based on that command, coprocessor will take the data from the external memory and might require some massage and prepare data ready for the vector pipe. And you design an ACE RVV low store instruction that will take that data from the coprocessor. And this interface is much faster than accessing the data through the L1 or L2 cache and the CPU, the BIU. All right, we're going to talk about the feature of ACE. You can design a single or multi-cycle scalar instructions. Or you can even vectorize those instructions by looping them many times as well. We're going to give an example later. And you can put those custom instructions in different categories that it's like you have a multiple pipeline so that they will not block each other. And you can, for the operand part, you can use a standard operand like immediate, GPR, just like any regular scalar instruction. And you can also custom design the ACE register and ACE port and ACE memory as well with arbitrary width and numbers. Or you can imply the parameter so that you don't need to take the additional opcode. So with all this input, instruction and operand, you can put them through a 2-chain NDIS provide called Copilot. The Copilot will automatically generate the opcode assignment, and all required tool and simulator are generated. The RTL code for the instruction decode, operand mapping, dependency checking, and input access and output update automatically generated. If you have a shared logic, it also will be implemented as well. And you will also provide the waveform control file for you. Here is the ACE development flow. So if you already coming to the design, you already know what you want to implement for the ACE instructions. You just need to go through the right-hand side of the flow to implement the ACE RTL using the NDIS Copilot tool. Evaluate the PPA, and keep iterating on this loop until you're satisfied with the requirement. But for most people, that you don't know what you want to accelerate. So you need to have a tool to help you to profile your software application and identify the timing critical code. Once that's identified, you can define your ACE instruction with the cycle count defined. And once that's done, you will iterate this flow until you're satisfied with the result. Then you can move on to the right-hand side of the flow to implement your ACE instructions. Okay, we're going to talk about the Copilot tool later. And now I'm going to talk, for this page is an NDIS IDE. This is the help you to analyze your software program to identify the critical hotspot. Upper left corner in the directory structure, you can have multiple implementations. And in the middle window, it shows the C code of your application. And the middle lower window shows you the assembly code. And the upper right corner window, it shows the cycle count between the trigger point. And the right middle window show you the cycle count within each subroutine. With all this information, you can identify the hotspot and to make a decision on what type of custom instruction you want to make. Okay, in order to design the ACE instruction, you need to have ACE description, which describes the instruction interface and behavior. And also you need to implement RTL code for the instruction operations in concise Verilog or system Verilog format. So Copilot tool will help you to implement this ACE instruction. It takes, on the left-hand side, C code, Verilog code, and the attributes in, and it will spit out extended RTL, extended ISA, also extended toolchain like compiler, assembler, disassembler, debugger, IDE. Since the C code and Verilog code are implemented with different people, then you want to make sure those two are equivalent. So Copilot will generate a verification environment to help you to verify extended instruction set simulator and extended RTL. After you're done with this verification, that will give you a high confidence that those are equivalent. Okay. Here is an example for ACE design using 8-bit multiply and add instructions. On the upper window, the blue letter is the instruction name. And the OP defines the input and output of these instructions. And CSIM defines the functionality of this instruction using C semantic. In the lower portion of the window, it shows the design using Verilog code. And you don't need to write a completely Verilog code due to the input-output already defined by the ACE description above, and it will automatically generate it for you. Once you're done with the Copilot, Copilot will automatically generate an intrinsic function for you. So you can put that intrinsic function back into your software, and you can run your simulation using your new intrinsic function to see the performance enhancement. I mentioned earlier, one of the functions of the ACE instruction is the vectorization instructions. We use the same instruction we did on the previous presentation, the previous page, 8-bit math instructions, and we're going to vectorize on that. So the upper left corner window have a VEC that indicate that's a vector instructions. And the thing we changed is instead of using GPR as the input parameter, we're using the X memory, custom memory as an input parameter. And the loop type indicate how you want to loop these instructions and the number of loop that you wanted to loop them. The strike command tell you the memory address automatically increment by 1 for each iterations. And for the CSIM, which is the functionality description, and the Verilog code doesn't change within each loop, so you don't need to change them. Let me recap on the what I have presented today with the NDIS custom extension. ACE delivers the software configurability. It provides performance enhancement and power efficiency. And Copilot eases the development of the custom extension. And NDIS side IDE helps software analysis. And Menta brings in-system hardware configurability to the ISA. It provides all the benefits of the ACE, plus hardware configurability provide performance enhancement. It also provides in-situation flexibilities. Gareth from Menta will tell you more about this. Gareth?
Thank you, Bing. So I'd like to talk about the actual practicalities of an SoC implemented with a RISC-V instruction set extension and an eFPGA. So my name is Gareth Baron, and as you know, I'm the Director of Applications Engineering here in North America. So a little bit about our company. So Menta is a European-based company, and we provide eFPGA IPs on standard cell-based architectures, along with supplemental design tools. Our eFPGAs provide an IP design targeting any production node at any foundry, and we have a simple design flow integration of soft or hard IP on standard cell technologies. It's an easy-to-use FPGA design tool flow, and we have this tool called Origami Programmer, which I will talk about later. And we have proven technology with a 10+ year pedigree. So firstly, what is an eFPGA? Most of you probably know what an FPGA or a monolithic FPGA is, such as Xilinx or Altera. Typically, they're devices that have an I/O ring, which is SerDes, LVDS, TTL, CMOS interface to the outside world. And then they have a matrix in the middle, which is the core. And basically, an embedded FPGA is just the core. So let's look inside an eFPGA and what it contains. So we have embedded logic blocks, which basically is your digital logic, and that'll contain lookup tables and D flip-flops to synchronize your digital logic. We have DSP blocks, and the DSP blocks are typical multiply accumulate kind of DSP, but also Menta has an added advantage that we provide FIR and IAR pre-processing inside these DSP blocks. And the DSP blocks are actually configurable at design time, so we can have different size DSP blocks to be optimal for your design. We have a configuration interface, and this configuration interface allows you to program an uncommitted array with your design, such as a custom extension instruction. Then we have a DFT interface, and Menta can get 99% plus testability in their designs because we use a D flip-flop based architecture. So we're fully scannable and we can verify for defects. We have the I/O ring, and the I/O ring is basically a registered input-output bank, which allows you to close timing at the SoC level. We have embedded memory blocks, and these embedded memories basically use third-party or foundry memories. And what we do is we put a wrapper around this, and this allows us to intelligently use the memories in the design during synthesis and place and route. And then finally, we have these embedded custom blocks. And these embedded custom blocks are basically hard macros that are provided by the customer. And it may be some clever technologies such as analog multipliers or some RF modulation scheme that's done in the analog domain and then demodulated, or some other mix of technologies which we haven't heard of yet. And that can be embedded into the array so that you can basically use the array in a custom way and change it on the fly. What's not shown on this diagram is that we have a routing grid and switching grid that's actually part of the embedded logic blocks. This allows you to route in an XY fashion across the whole part. Okay, so how does an eFPGA map into CPU register space? As Bing mentioned, they have the Andes custom extension interface, and that provides a register interface. Those registers would be a set of source registers and a destination register in the interface. And then what we would do inside the eFPGA is do the math function, and whatever function that is. In this case, we're doing instruction extension. Okay, so how does it integrate with the CPU? At the SoC level, we have the CPU with the ACE interface connecting to the Menta eFPGA. That'll have clock and reset and the instruction, source and destination registers, and some other I/O signals for control of data flow. Then we'll have a programming interface, which will allow you to program the eFPGA with its bit stream. And then at the top level, we'll have a bus interface, which will connect to the CPU. And this is up to the SoC design team on how they wish to implement this. So in this example, I'm showing AHB or AXI interface, and I would put this in a CPU space memory map, and then the CPU can access this memory map, with ports to talk to the eFPGA programming interface, and you would read and write data to that interface to program the bit stream into the eFPGA. So typically the eFPGA is uncommitted at this point, and then when you program the bit stream, the FPGA becomes committed and becomes a functional unit of the device. Okay, so how does an eFPGA get its bit stream? So Andy's ACE tool produces the RTL and an interface for that. And then also the user will provide instruction RTL that actually implements that instruction that they require to use. The Origami tool will perform logic synthesis, and it'll take in the ACE and the user RTL, and they get mapped into logic and DSP along with memory. So we do place and route, and we do have high optimization within our tools for that place and route. We have timing extraction, and we have bitstream generation. So just a high level view here, you have the RTL, the ACE RTL and the user RTL goes into Origami Programmer. Origami Programmer produces a bitstream, which will then get committed to the array. So what we'll do is we'll show you a process of us going through a design. And we're using a custom CRC instruction being implemented in an eFPGA as part of a CPU extension. What I'll do is I'll play a video, and I'll stop the video as we go through. Okay, so this is the input file to Copilot, and Spring showed you we actually have some various information in this file. So first we have the CPU definition, and this tells us, what the definition is and how it's optimized. In this case, it's optimized for frequency. We have the instruction configuration and how the instruction is to be encoded, and in this case, it's the 3-stage pipeline. And then what we have is the instruction definition, which is how the profiler understands how the instruction works. And this is used by the C compiler tools, Andy's tool environment. Okay, finally, we have the Verilog, which is basically implementing the instructions. So here we can see it's an LFSR, which is implemented in parallel as system Verilog in this example. Okay, so now we're running Copilot. It generates all the RTL. Here's the directory it generated. Then here's a full list of the ACE Verilog files that will be synthesized. So now we're starting our Origami tool set. Open the project. Okay, so I'll just pause this quickly. So this is the Origami programmer interface. It's a GUI, and the tools can actually be run as a GUI from the command line or through TickleScript within this GUI. And I'll go through the various panels just so you have familiarity on how these tools work. So on the left here, we have the input files. So the top file, which says eFPGA ARC for ACE, is actually a Menta architecture file. And this Menta architecture file contains a full definition of the array and the mix of components within that array. For instance, you may have logic, DSP, memory, and the size of the array all defined. And this is something we would define upfront as a team to figure out what the best optimization is for your design and your SoC. The next one is a timing requirement. So we basically look at typical timing, and then we'll have input files, which is shown with a blue dot there. And then we have design constraints, and the I/O constraints which define the periphery I/O. The next window is the process window, which shows the synthesis, place, and route tools. There's actually a lot going under the hood here, and the tools do a lot of clever stuff under the hood. You know, they take the synthesis and then they'll actually look at the architecture and figure out how to do the placement and optimize that to get the best placement. And they'll make decisions on whether it should be in logic or whether it should be in DSP, and optimize this. Okay. Then we have the timing and the output tools. So we generate port locations is actually to generate the IOs initially. Typically, you generate the IOs at an initial design, and then you start using the IO constraints once you've edited that. We have a timing report, which will produce static timing reports, slack timing. Then we produce simulation models, which will be SDF back annotated simulation models. And then finally, the bitstream generation, which is used to program the array. Okay, these are the display tools, which just basically show in the GUI window what items to highlight and show and switch on and off, so you can actually figure out parts of your design. Then here we have the progress window, and this shows various parts of the compilation stage, etc. And you can basically watch what's going on, see if there's any errors or progress reports. Here we have the layout window, which just shows you graphically what the chip looks like from the top level. So what we're going to do now is we're going to go and get the design. We're going to add that directory that I showed you earlier. Okay. The tool actually recognizes all the types of file. So here we can see that it's recognized Verilog and system Verilog files, and it knows what flavors they are as well. As you may or may not know, Verilog and system Verilog and VHDL all come in different versions as the standards have improved. And here it recognizes that you have version 2005 Verilog and 2017 system Verilog. So here the tool actually extracts the top level, and it recognizes the hierarchy and automatically populates the top level design. So now we're importing this into the design. So we're going to open the IO constraints, which defines all the IO boundaries. And as you can see, it's in northeast, southwest kind of configuration, cardinal letters of the compass. And then we define which IO ports and pad numbers they are. So now we're going to run a tickle script of the synthesis real time. So now it's running the synthesis, which is producing a netlist from the Verilog files. It's doing the placer. Okay, and now it's doing the routing, and there it's finalized and finished the place and route. So here we can see a fully final design. Okay. The next thing we're going to do is generate the bitstream file. And we'll look at the bitstream file just to show you. So it's an ASCII file. Basically, what would happen is the software would take this file and it would use this inside its code to actually write to those ports to program the array. Okay, so I'll go back to the presentation now. So what do we get from all of this? So here we have the native instruction profile showing us 372 cycles on the left-hand side. Then on the right-hand side, we have the accelerated function in hardware showing 7 cycles. Now, this doesn't take into account that the bus speed is half the speed of the CPU speed. So the profiler doesn't understand that. So basically, we multiply this by the speed of the bus. So we have it 2 times, decrease in speed. So this would be 14 cycles. So this will give us about 27.5 times speed up. And this is really, really fast because you're unrolling a loop inside the CPU and running it in parallel in hardware. Okay, so the benefits of a custom RISC instruction set architecture extension with an eFPGA is it allows the custom instructions to be user-defined. So you may have some SDR, software-defined radio extensions. You may have algorithmic acceleration, CPU high-performance acceleration, example for AI, or you have iterative function speed up, and that's an example we're showing with CRC. That you have basically a loop that's unrolled in hardware and it's iterated at high speed, physically in silicon. Okay, the customization will suit different applications, and automotive may be an example, using it for a reconfigurable engine management system. Telecom provides field upgradable software-defined radio protocols. As you probably know, telecom basically deploys protocols and upgrades quite frequently, and deploying this in the field and mass deployment is actually quite an expensive thing to do. The other advantages you get from an eFPGA is you can run these at wire speeds on the silicon. You don't have to come off the silicon, off the CPU on a PCB into another part and then do that process. You actually run this inside the silicon. So you're running this at wire speed inside the silicon. Another one is defense and space and remote upgradability. So satellites are obviously, you can't send a field applications engineer out to the field to replace stuff or change parts or do software upgrades. So you can do this all by telemetry, and that's an advantage. Another advantage is that we have is that eFPGAs can be put in a rad-hard process. So this allows you to do a rad-hard design that can be used in the defense and space industry. IoT and IIoT can do cryptography, acceleration, obfuscation, and edge functionality. So the key takeaways here is that ISO extensions are flexible. So we've seen the ACE tool flow from Andes. Acceleration can be optimized after the silicon tape out. So what we have is we have a basically uncommitted array that we predefine upfront to figure out what we need. And then we would basically commit that array after the fact. And this can be done later down the design. This can be done as upgrades to technology as it's out in the field, as part of a software pack. So you have the complete capability of upgrading your silicon in the field. So you can get longevity out of your parts, and you can get full functionality and different functionality out of the same part. And then we have a simple tool flow. As you saw, I ran the Copilot from the command line and the Menta origami tools. The Menta origami tools, I just want to note, are purely owned by us and can be deployed or licensed to any other third party. We don't have any restrictions on these tools. And the other thing we have is the ability to develop stuff internally on those tools. So if there's custom things that you need, we can develop those as well. Okay, so thank you very much for listening to my presentation, and we'll now go over to the Q&A section.
Okay, we do have some questions. First question, are the eFPGA IPs fixed in size?
I'll take that question. Okay, so eFPGAs are not fixed in size. They're fixed after committing to silicon, but during the design time, we can define that array to be any size that we want. And this comes down to how much area, real estate, and how much resources you require. So one of the advantages of Menta is that we can actually define that size to be anything you want. So we don't have a fixed block size and fixed macro size that you have to define. And this allows us to actually, optimize it for your design, and we can go through an iterative cycle. Menta can iterate this very, very quickly so that you can actually try different designs, different architectures. Maybe you want to be DSP-centric, maybe you want to be memory-centric, maybe you want to be logic-centric, and we can try all those different flavors and give you those different flavors to play with. So that's something we would discuss, as part of the design iteration. So hopefully that answers that question.
Another question, how many companies switch from Eclipse to VS Code? Do you have a plan for this?
Bing, I think this question's for you.
Oh, actually, I do not know the answer, so I can get back to you on this.
Yeah, you can email it.
Yeah, Dan, can you forward me those questions? Thank you.
Will do. Another question, how are the register dependencies handled with the ACE instructions?
Oh yeah, the architecture implementation automatically keep track of the register dependency, so it's transparent to the users. As long as it will follow the this program sequential order, so it just works like any other program.
Okay. Another question for you, Gareth. Are you using an API for Menta's eFPGA part of the code, or should the user know how to use the eFPGA software?
So the user should know how to use the eFPGA software. We would provide that. We'd provide training for that as well. So it's not an API. This is actually an interface. The actual eFPGA software can be run in multiple modes. So the workflow a lot of customers use is actually they run it from the command line in their standard workflow as part of their SOC work, and they'll basically call out the eFPGA tools as they go through the workflow. So there's multiple ways to use this. The GUI is typically the way most people use this to start out with until they refine their process, and then they go into more an automated pickle kind of format. So it's not an API, so to speak. It's actually calling physical tools from the command line.
Okay. Another question, what about SIMD and VLIW instruction? How is it managed?
Well, those instructions are custom, is a user defined. You can define whatever the instruction you want it to be. As long as you can describe in C, you can write it in Verilog, then we can implement it.
Okay, another question for you, Bing. Would ACE implementation gate my overall processor frequency?
That's a good one. We detach the frequency of ACE pipeline with the core pipeline. So your ACE pipeline can run as slow as you want it to. You just create longer latency. So the interface between the ACE and the core pipe will signal are asynchronous. So you will not gate the core frequency.
Okay, and there's a follow-on. How can I try out the ACE implementation?
You need to contact our field sales. So please come to Endis website. I think www.endistech.com, technology.com. And find your local sales, please. Thank you.
Okay. Does Menta have any more information on eFPGAs and how they work?
Yes, we do. So we're actually working on releasing a white paper at the moment, and this is going to be published very soon. And what we'll do is we'll provide this eFPGA white paper to the public, and please send us an email, and we'll basically give you information when it's released. And this will go into more detail about eFPGAs and generally how they work.
Okay, there's another question. I'm not sure if I have this right, but it says, how an exception from eFPGA are transferred to the CPU?
Oh, I can handle this. Yeah, you have that description, right? Yes. Since the ACE is being dispatched at the write back stage, that means that they will not have any exception. Already went through all the exception check already by the time issued to the ACE pipe. I hope this answers your question.
Okay, I have a quick question. How does Andes and Menta, how do the tools integrate?
Gareth, I think you can talk about this one.
Yeah. So the tools are basically run at the command line in our case. So you basically they're run under a common framework, and in our case we're using a Linux platform. So that's really the integration. The integration is basically I suppose the wall or the fence is that we're basically passing Verilog and synthesizable code over from Andy's ACE tools over to the Menta tools. And then the Menta tools basically taking the Verilog or VHDL as required and synthesize that. We're kind of agnostic as far as the RTL. So we don't mind, and the Andy's tools, and they produce system Verilog or Verilog. So that's really where the integration is.
Okay, we have one final question. This is for you, Gareth. Oh, no, I'm sorry. This is for you, Bing. How is the intrinsic function instantiated?
So intrinsic function is just like a function call. You just put that functional call in your C code, just like any other functional call. That's it. It's simple. And if you go back to my presentation, one of the slides show example of that.
Great, thank you. That concludes our webinar. Thank you all for participating in the SemiWiki webinar series, and have a good day.